Okay, welcome everybody. Today we are going to have Agustina Pereyra Grau. She's a PhD from Universidad de Buenos Aires. She's with the Instituto de Astronomía y Física del Espacio, and she will be speaking about hidden symmetry from extra dimension. So, Agus, all yours.
Okay, thank you. So yes, I'm going to talk about hidden symmetries from extra dimensions. That is the title from a paper that we have recently published together with my supervisors, Diego Marquez and Carmen Núñez. Well, first, I'm going to give a little motivation to this work. First, I'm going to talk about alpha corrections. So as most of you probably already know, string theory predicts an infinite series of higher derivative corrections to supergravity. And these corrections scale as this alpha prime, which is essentially the inverse of the tension of the string, or in other words, if the square root of this alpha prime is the length of the string. So in order to make this expansion, for it to have sense, then we consider this length of the string a lot smaller than the typical length of the curvature of the fields of the effective theory. So the leading order in this effective theory is supergravity, which here it has two derivatives of the fields. Here the superindex indicates the number of derivatives that the theory has. And here I wrote an example for of a two-derivative theory for the universal sector. That is the common universal sector that every string theory has. So here you can see that it has two derivatives. We have the Ricci scalar, which has two derivatives of the metric. We have a contraction of derivatives of the dilaton. And we have a B form, a 2 form, that it's included here as the derivative, as this H curvature, which is the derivative of the 2 form. And well, this is the Ramond-Ramond field. So you can see that this action all contains two derivatives. But if we want to consider some string effects, then we have to go to the next order in these corrections. And I wrote here an example. That is the case of the type 2 superstrings. For this case, we have that the first corrections, the first and the second correction, are 0, and the corrections start at cubic order in alpha prima. So here, this means that it starts with 8 derivatives of the fields. And I wrote here an example of a well-known correction for this type 2 Neveu-Schwa sector of superstrings, which is it can be written in compact form with this Riemann minus, that it's the Riemann minus some derivative of this Ramond curvature. So we can see that this Riemann minus is we have it in 4 factors, like 4 Riemanns of this kind. So this involves 8 derivatives. And these T8 are just some tensors that indicate how we contract the different indexes of these Riemann minus. Okay, so in principle, we can compute these alpha corrections as using string scattering amplitudes, but that can be very difficult if we go, especially in 4-point amplitudes or for the Ramond-Ramond fields. So that approach can be very complicated. And so instead, we prefer to look at the symmetries that we think that are going to be in the theory. So we have some very good symmetries we can use, for example, diffeomorphism invariance, or gauge invariance, or supersymmetry, or dualities. But many times these are not enough to constrain all the possible terms that appear in these alpha corrections. So it is in this context that I started studying these hidden symmetries that I'm going to explain later what I'm talking about really. But these symmetries that are symmetries that come from dimensional reduction. So consider we have a theory that is defined in big D dimensions, and we reduce it. We perform a Kaluza-Klein reduction on a torus of dimension D, small d. So we obtain a theory in lower dimensions. So the thing is that this original theory can have some symmetries, for example, diffeomorphism or gauge invariance. And well, some of the symmetries, when we perform the Kaluza-Klein reduction, are going to still be present in this lower dimensional theory, but there might be some symmetries that are broken. So the observation we did in this paper is that these broken symmetries are actually realized in the lower dimensional theory as global symmetries, and that these symmetries are not obvious from the point of view of the lower dimensional theory. But if we know that this theory comes from a theory of higher dimensions, then we can impose this symmetry principle in the lower dimensional theory and use it to fix interactions for the lower dimensional theory. So this is like hidden or symmetries for the lower dimensional theory that were inherited because of the Kaluza-Klein reduction of a higher dimensional theory. Okay.
Sorry, can I
Yes.
ask you a question? You have these hidden symmetries because you are like taking truncation in the Kaluza-Klein reduction, and that's why when you take like truncation, okay, yes, you, I agree that you will have less symmetries than before. Is because of that, or you always have these hidden symmetries when you do a reduction?
Well, maybe now I'm going to make more explicit what I'm talking about. Maybe it's going to be more clear just 2 slides from
Okay,
now.
okay. Okay, okay.
So, okay. Yes, this is just for you to get the general, the big picture of what I'm going to talk about, but now I'm going to specify better what I'm going to be doing exactly. Okay.
Can I ask if this is
Yes.
related to the torus, or this could be just more general in case you reduct in a different manifold, for example?
Well, we only explored the case of the torus. We didn't go far beyond that, and because it has the advantage that we keep only, well, we didn't explore any other more than that. So I'm gonna stick to this to this simplest case. Yeah.
Sorry that we are anxious people.
No, it's okay. It's okay. Okay, so basically the outline of the talk is the following. Here, first I'm going to define what I'm talking about when I talk about this hidden symmetry, that is alpha symmetry. Then I'm going to show you some applications that to pure Einstein gravity, where we use this alpha symmetry principle to constrain the pure Einstein gravity. And then the case of the type 2 theory. First, I'm going to show you how to, again, use the alpha symmetry to obtain the Tura derivative action. And then I'm going to talk a little bit about the higher derivative corrections and what are the limitations of this alpha symmetry to obtain these higher derivative corrections. Okay. Well, first, now I'm going to define a little better what is the alpha symmetry I'm talking about. So first, we consider we have a d-dimensional manifold that it's going to split into n dimensions times torus in small d dimensions. So in order to make the conventions clear, here I use the Greek indexes to this run over the higher dimensional space-time. And then the Latin indexes are gonna, the I, J, K are gonna run, are gonna be for the external n dimensions of coordinates. And the M and PQ are gonna be the ones labeling the internal compact space coordinates, okay? So now consider we have a tensorial density P that in principle, it depends on the external coordinates X and internal coordinates Y. and it has a weight W. So here I write the Lie derivative of this tensorial density, that it can be written this way. So now what we do, since we want to perform a Kaluza-Klein reduction, we are gonna propose an ansatz for the V tensor. And we see here that the components of the V tensor cannot depend on the internal coordinates, only on the external coordinates. This is in order to be consistent with the fact that we just want to keep the massless modes here. And so this is, we're only keeping the dependency on the external coordinates. And for the parameter side, which is the generator of the higher dimensional diffeomorphisms, we can also split it into some n-dimensional diffeomorphisms that are the standard diffeomorphisms in the lower dimensional theory. We have some gauge parameters that are this lambda, and well, some general linear transformations in the compact space. These alpha here are just constant parameters, and that you can see that run over internal indexes. But what we are gonna focus our attention on is on these alpha transformations that are generated by these alpha parameters. These alpha parameters that have mixed indexes. So here this is an internal index and this is an external index. And it goes a little far beyond the standard n-dimensional diffeomorphisms, because here we have it's a constant parameters, and it depends on the internal coordinate in this way, but it is consistent with the Kaluza-Klein reduction, the massless Kaluza-Klein reduction. Okay. So for it to be consistent, we also have to constrain these parameters a little further. We have to use the fact that the contraction of these alpha parameters with the derivative in the external direction has to be 0. So in this way, we don't get any internal dependencies from performing the alpha transformation. So when we compute, we replace, only look at these transformations. We replace them here, and we obtain how the different components of this V tensor transform. And we see that this alpha transformation mixes all the different components of the V tensor in a very non-trivial way from the point of view of the lower dimensional theory. So here, for example, the external component mixes with the one component out of the diagonal. And well, we have some different combinations of the different components. But none of these depend on the internal coordinates, which was the important thing we wanted to make, for it to make consistent the whole Kaluza-Klein reduction. Okay, so now if you consider a scalar in d dimensions, for example, the Lagrangian, and we compute the alpha transformation of this Lagrangian, then we get this, and then we are specializing for the alpha transformations. So these psi parameters are just the alpha transformations. And when we compute this, we obtain that this is just the derivative of the Lagrangian, but this derivative is contracted with this alpha parameter. So here we are using, if you use the constraint that this has to be 0, then the whole thing vanishes. And then this alpha transformation for the Lagrangian is 0. So this means this is an invariant. And so a dimensional scalar, like the Lagrangian, is going to reduce to an invariant also in the lower dimensional theory. So this way we can define a global symmetry principle for the reduced theory that can be used as a principle to fix couplings. So seeing that the theory is going to be invariant under these alpha transformations, if it comes from a higher dimensional one, then from the point of view of the lower dimensional theory, we can use this as a global symmetry and use it to constrain the couplings of the lower dimensional theory. Okay. Is this more clear now? Okay, great.
Yeah.
Okay, so now that I explained what I was talking about, I'm going to use this principle, this alpha principle, to obtain the pure Einstein gravity, the two derivative, what we obtain when we use this alpha symmetry in the pure Einstein gravity. So here we have the parameterization for the metric. The first thing we do is parameterize this metric in the higher dimensions, as we did before for the V tensor. And we see that here we already split into the different degrees of freedom that this higher dimensional metric tensor has. But all these fields are going to depend only on the external coordinates. Here we see that we have the metric in n dimensions, and we have some gauge vector fields and some a matrix of scalars, that these are just scalars in the lower dimensional theory. So, well, we compute the alpha transformations just as we did before for the case of the P tensor. So we do the same thing here, and we obtain how these different components are connected to each other via alpha transformations, and see this is very non-trivial since we have the metric connected to the gauge vector fields. And well, so what we do next is we propose the most general Lagrangian that is invariant under n-dimensional diffeomorphisms, gauge transformations, and general linear transformations in the compact space. So here we propose, what we get when we propose that is this Lagrangian that you can see that it has some coefficients that are still not fixed. And that we are going to fix using the alpha symmetry. Here we have the Ricci scalars, the kinetic term for the gauge fields, and the terms that have to do with the scalars. So now we want to constrain this, we want to obtain these parameters using alpha symmetry. So for that, we compute the alpha transformation for each of these of the terms of the Lagrangian, and for that we use the way the metric transforms and the way the gauge abelian field transforms, etc. And we obtain these things. And when we plug this into the Lagrangian, we compute the alpha transformation of the Lagrangian, then we get this over here. And if we want this to be 0, then this constrains what the parameters are. So we obtain the couplings, the value of the different coefficients, imposing alpha symmetry. Okay. So, okay, if this is clear, this is more like a toy model to show you, because we also did this in the case of the Type IIA supergravity. I'm going to talk about this now. So in this...
Sorry, just to be sure, because it was like a kind of my question before, so to see if I understand. So these high symmetries comes from the compact manifold symmetry. I mean, where you have the whole all the space, you compactify. These symmetries come like for the ones from the y coordinate, the interior coordinate that are from the compact space, right? So it's like from there comes these high symmetries.
Yes, it comes. Yes, exactly from this. This is the alpha distribution. Yes.
Okay.
Yeah.
Okay, it's not okay. So it's not from the truncation. So okay. Now I understand it.
Yeah. Well, this is consistent with a massless truncation. Okay, because this is what we can add here in order to not get dependency on the internal coordinates. Like this is enough to get that. But we could be more general and just perform a Kaluza-Klein. We could compactify directly, and this this will just have standard diffeomorphisms that will depend on the different components of the internal and external components. But the thing is that we don't want to perform a compactification. We want to constrain the action, but using this minimal, say, transformation. That's it's a global kind of transformation. I don't know if that's more clear.
Yes, better. Thank you.
Yeah, you're welcome.
Agustina, so this transformation lives in the isometry group of the torus?
Well, I think it's more constraining than that, because we have to say that we are keeping the massless modes.
So, but it's a subgroup of this or something like that?
Yeah, right.
Okay.
Yeah.
Okay, thank you.
Okay. Well, so I was going for coming here. So the type 2 supergravity. I'm going to explain now this example. Here we have the 11-dimensional supergravity. So maybe you know that you can obtain the type 2A supergravity in 10 dimensions by circle compactification of the 11-dimensional supergravity. So the 11-dimensional supergravity looks like this. Here we have the Ricci scalar. We have this curvature for the 3 form, and some the Chern-Simons term. So, well, the fields we have are this metric G mu and the 3 form A, and this 3 form has this gauge transformation that is given by this lambda, and the curvature, well, it's this one. So the 11-dimensional diffeomorphisms now here act as usual for the metric and for the 3 form. So now we do the same we did before. We consider a Kaluza-Klein ansatz that's for this metric, and we get this standard Kaluza-Klein ansatz, which the fields again do not depend on the internal space coordinates. And we see the difference from the previous example here is that we don't have anymore a matrix of scalars. We only have one dilaton here. So this is because the compactification is done now in a circle. So there is only one degree of freedom related to this. So it's going to be this only dilaton. Okay, and now we have, besides the metric, we have this 3 form that it also that decomposes into a 3 form in the lower dimensional space. And there's also a 2 form that comes from taking this coordinate in the internal space. So this is basically the content of fields we have in this theory. And now we write the ansatz for the psi parameter. But now we omit to write to skip this internal index, because there is only one compact direction. So we just write it this way. And also I write the general linear transformations in the compact space in this way, using this rho as a parameter. So because I'm the Lagrangian yet to satisfy this invariance under this. So, well, here we have the gauge parameters, and we see how the fields transform under these gauge parameters. We have a 1 form with this lambda transformation. We have a 2 form with the standard gauge transformation. But for the 3 form, we see that there is an extra term that comes because there is this 2 form. So in order to define gauge invariant curvatures, we have to add this. For the standard curvature of the 3 form, we have to add this term that has a 1 form and the Ramond curvature. Well, this is the Kaluza-Ramond curvature. It's just the derivative of these two forms, and here we have the curvature for the one form. Okay, and we now do the same thing as before. We propose the most general two derivative Lagrangian that is invariant under the diffeomorphism and engaged transformation in 10 dimensions, which is this one. And we see here that we left these functions can still depend on the dilaton, because we didn't impose the raw invariance yet, the invariance in the under general linear transformations in the compact space. So this is defined up to some functions of the dilaton, and now we are trying to constrain this. So we write the the raw transformations for each of the components of the fields, and the alpha transformations, of course, using the constraint, which that is the contraction of the parameter with the derivatives has to be 0. And so, well, we write the alpha transformations for each of the fields, and then we write it for each of the different curvatures. We also write it for the determinant of the metric and the transformation for this exponential of the field of the dilaton. So because we want to construct an integration measure that is invariant under these transformations, but we can see from here that we cannot construct a measure that is invariant under both alpha transformations and rho transformations. So we are going to just ask to have only that the measure is invariant under alpha transformations. So we impose this, and we obtain that the function here that depends on the dilaton is this exponential of minus 8/3 of the dilaton. So this is what we would expect that from simply reducing the 11-dimensional measure to the lower dimensional one. Okay, so with this we can obtain the invariant measure under alpha transformations, and so we can, by asking that the action is invariant under raw transformations, we obtain what the functions for each of these terms was. The dilaton dependent functions are just, well, what we wrote here. And well, so we are left with an action that it's defined up to some coefficients, gamma, this gamma 0, 1, etc. And now we are going to constrain those coefficients using alpha transformations. And here I'm gonna split a little bit to see how alpha transformation are connecting the different parts of this action. So here I wrote the terms that descend directly from the 11-dimensional Ricci scalar. So the Ricci scalar, it was this one. So after the compactification, some of them are going to descend from that term, which are these ones. These terms descend from that, and you can see that then alpha transformations are connecting these different terms. So that we can fix the coefficients up to 1 gamma 0 coefficient, a global factor. So, well, we have this, and then there are terms that are going to come from this term, the 3-form curvature, which is going to go back from this term. So the ones that come from this term are these two terms, and that relate to each other via alpha transformations. And so we can fix the coefficient that relates the two, right, in this way. And also there's a term that descends directly from the Chern-Simons term. So by calculating the alpha transformation, we can see that these two terms are going to be related via alpha transformations. We have to use this identity to see more clearly. But we finally get that the coefficient that relates these two terms is going to be, well, this one that I wrote here. So we are left with this action that is the most general action in 10 dimensions that has two derivatives, and that's it's invariant under 10-dimensional diffeomorphisms, gauge transformations of the p-forms, and alpha transformations. And also rescales homogeneously under Pro transformations. So we get this, and we here can clearly see that these coefficients are not yet fixed. They are not fixed by alpha transformations because these different terms are not related with each other via alpha transformations. So this is all we can get from imposing these symmetries. Well, of course, this global factor here, we don't really care about it, so we can just set it to 1. But this can be fixed via beta symmetry, which was studied in these papers. That is like a generalization of ODD symmetry. And well, we get, if we use this beta symmetry, we get the standard coefficient that goes with, we can obtain it in the, we saw it in the universal sector. So, well, the only thing that it remains without being defined is this coefficient that we should know the original theory to know what is the value of this thing. But, well, the important thing here is that you can see that the Neveu-Schwa fields are related to the Ramond-Ramond fields via alpha transformations. So this is very important because we can then use this in order to make predictions of the higher derivative corrections of this theory. Okay, so I'm gonna talk about now about some higher derivative corrections. Okay, so I said before that this was the known alpha correction for the type 2 theory. And this has this Riemann minus that it can be written in terms of the Riemann minus this derivative of the Kaluza-Ramond field.
So can I ask something?
Yes.
When you discuss about these zeta 3 terms, they have this form Riemann minus to the fourth, but for the Ramond-Ramond fields also you have terms with zeta 3.
Sorry, I didn't hear.
With this zeta 3 parameter for the R fields, they have this kind of terms as well, because you are trying to say, I think, that you want to relate these terms via alpha transformations, right?
Yes.
But the other terms also has a transcendental number, this zeta 3.
Yeah, well, if we want this, the idea is that if we want this to be a theory that has an alpha competition, then it really should.
But it was computed, do you know?
Via
scattering amplitudes or beta functions.
It was kind of difficult to relate our results to those computations. So I'm not so sure.
Okay.
I don't want to say something that is wrong. So this is what, here we are going to see that the Ramond-Ramond, that we can obtain the alpha competition of this Neveu-Schwa, or what should be there if using the alpha principle.
What I am trying to say is that if you use the alpha transformation, you are going to turn this Riemann to the fourth term into terms which are like p-forms, right? P-forms, products of p-forms.
Yeah.
Times this zeta 3. And my question is if these terms exist in the literature or not, because if they don't exist, if they were computed by, I don't know, scattering amplitudes and they haven't appeared, then it's like alpha is not a symmetry at that order, right? That is what...
Well, that could be a possibility, yes.
That is what I am not understanding. So far, you are going to transform this, right? You are going to take these terms and you are going to transform. Okay.
Exactly. Okay. Yes. We expect that alpha symmetry doesn't receive corrections, but okay. Well,
Yeah, because you can have corrections, for example, transforms as some P forms in the lowest order with some correction of this transformation and kill these contributions.
Yes, exactly.
Okay.
So as I was saying, here we have this Riemann minus. So that this is what it is known, right? The Neveu-Schwa correction of the type 2 theories. So here I'm gonna write this expression a little bit more in a more compact way. If we change these indexes, I and j, like we take two of these indexes and we rename it with an alpha, then we see that this Riemann tensor is symmetric under the interchange of two pair of indexes, which is because of the Bianchi identities. And this term is antisymmetric under the exchange of this pair of indexes. So what we obtain, knowing that these T8 are symmetric under the exchange of two indexes, we obtain, for symmetry reasons, that this term can be written in this way. So here we have products of 4 Riemann tensors, and here we have products of 2 Riemann tensors, and here we have products of the 2 Kaluza-Ramond fields, and here 4 Kaluza-Ramond fields, which are written more explicitly here, what we mean for each of these terms. So, okay, so as I showed you before, the Neveu-Schwa terms are related via alpha transformations with the Ramond-Ramond fields. But the thing, these 3 terms are not related with each other via alpha transformations. So we can study each of these terms separately, and I'm going to show you the alpha symmetric completion of this quartic Riemann term. So here I wrote the Riemann term, this explicitly, and the thing is that this has a very obvious 11-dimensional uplift. So here the procedure is going to be a bit different compared to what we did in the previous cases, because computing all the alpha, all the invariant terms that could be here, it's very complicated. There are a lot. So we are going to take another approach, and here we write the the uplift of this Riemann 4 in the lower dimensional theory to the Riemann 4 in the 11-dimensional theory. So when we compactify on the circle, then we get this expression over here that contains the Ramond-Ramond fields and the completion of this Riemann 4 term. So this, since we are strongly using that this thing we computed over here is an invariant in 11 dimensions. So what we write here, we can check, is invariant under alpha transformations. So this will provide an alpha completion of this term over here. So we can do the same in principle with the rest of the terms that appear in the alpha correction. But it is a little more tricky for the other things, because there's no such an obvious uplift. We are constraining here to only 4 for quadratic amplitudes. So here what we are going to do here is, now we propose the most general combination of 11-dimensional terms of this form. This is in 11 dimensions. It has 2 Riemanns and 2 derivatives of the 3-field curvature. So there is a basis of these terms that was obtained by Peters, Plewka, and Stern, and so we use it here. So we propose a general combination of these possible terms with some arbitrary coefficients b. Each of these terms is going to be an invariant, an alpha invariant. So then what we do is we are going to fix these coefficients by compactifying this. So this expression, I'm going to compactify it. And then I'm going to turn off the Ramond-Ramond fields. They are going to be 0. And we compare that expression with what we know we already know this is the correction from the Riemann to H2. So this is going to allow us.
Sorry, why up to 24? The sum?
This is all the possible terms that we can write here. All the possibilities of contractions of these two tensors.
Okay, but it's not. Okay, no, I was just asking if there's like some physical.
These are like unambiguous terms, right? Like all the ones you can have,
exactly,
excepting like Bianchi identities and blah. So it's not trivial that this is 24.
Okay,
yeah,
okay.
Exactly, it's not trivial, but yes, these are independent terms. Yes.
Okay, thank you.
So these so we obtain these b coefficients by imposing the reduction of these when we turn off the Ramond-Ramond couplings, the Ramond-Ramond fields will give us exactly this. So this is how we sort of eliminate all the ambiguities that we could possibly have. We want this to be exactly this term, exactly this. So this fixes all coefficients except for 2 of them, which it happens because these two coefficients, these two terms are of course invariant on their own, and when we turn off the Ramond-Ramond fields, these disappear. So this just leaves some arbitrary free coefficients for this. Okay. So then what we do is we try to see what are the corresponding terms in the M-theory effective action that is computed here in the same paper before, that come from the 2 graviton to 3 form amplitude in the case of M-theory effective action. So this was computed here, and this is what they obtain. And there are some terms there is a basis of terms that vanish at quartic order in a background field expansion. So this is also a source of ambiguities. But we only ask that we are reducing exactly to this when we perform the compactification. So what we do is compare both of the expressions, this expression where we've already fixed almost all the b coefficients, and we compare it with this expression, and that's how we can fix this set coefficients. And there's one that it cannot be fixed, but we just set it to 0. So in order to be in order to simplify the computations. So what we obtain is the 11-dimensional combination that leads exactly to this that we already know, as opposed to up to 5-point terms. So it's exactly this the reduction of what we obtain is exactly this when we turn off the Ramond-Ramond fields. And then, so we obtain the alpha completion of this term, the Navier-Stokes term. It can be written in this way. In this way, we have the couplings with the Ramond-Ramond fields. There are a lot of terms, so here this is a simplified expression for it. I'm not going to write all the terms, but we obtain the alpha completion of this term. This is what we should add in order to make this thing alpha invariant. Well, so we did the same with the other term but I didn't include it in here. But essentially, so in order to summarize a little bit, so I show you what alpha symmetry is, that it comes from internal coordinate dependent information in the higher dimensions, and that it can be seen as a global symmetry with some constraint parameters in the lower dimensional theory, and this allows us to fix the two derivative couplings in the Kaluza-Klein reduction of the pure Einstein gravity. We also did this for the half-maximal supergravity in 10 dimensions, but I didn't include it here, but it's included in the paper. And we performed we use the alpha symmetry to constrain the reduction of maximal supergravity in 11 dimensions to the type IIA supergravity. And we also, well, use the alpha symmetry in order to make predictions about the Ramond-Ramond higher derivative couplings that could appear and that can complete the Nevers-Schwann terms. And well, of course, this method has some ambiguities, and we explicitly showed what they were, but we try to make a simple choice of scheme in which we obtain the alpha completion of the Nevers-Schwann corrections involving the Ramond-Ramond fields. Okay, so this is it. Thank you.
Great, thank you, Agus. I will stop the recording.